Good morning and afternoon, everyone. Welcome to today's webinar, Anomaly Detection in Real Time Using Spatial and Temporal Analysis. My name is Alicia, and I'll be your moderator today. Before we begin, there are a few housekeeping items I'd like to review. Today's webinar is being recorded, and you are currently in a listen-only mode. You may submit any questions you have throughout the webinar via the Q&A or chat function in the lower right corner of your console. We will address everyone's questions towards the end of today's presentation. After today's webinar, you will receive a follow-up email with a link to the recording and slides. If you wish to contact us, please send us an email to team@memsql.com. In today's webinar, we will show how MemSQL supports spatial and temporal analysis on real-time datasets in anomaly detection applications such as fraud detection, predictive maintenance, supply chain monitoring, social distancing, metric tracking, and contact tracing. Today's presentation will cover how MemSQL can be used for geospatial queries on streaming time series data, intuitive time series querying with newly added time series functions in MemSQL, and detecting anomalies in time series with a spatial dimension. With that said, I'd like to introduce our speakers, Eric Hansen and Dominic Ravita. Dominic brings 23 years of experience across consulting, software development, architecture, and solution engineering leadership. He brings product knowledge and a senior technical perspective to field teams and customers. He has experience in distributed in-memory data grids, streaming analytics, integration, and data science. Eric is Director of Product Management of the MemSQL database. He is responsible for query processing, extensibility, and geospatial feature areas. He is a PhD graduate of UC Berkeley, was an Air Force officer, a professor of computer science at the University of Florida, and a principal program manager and developer for SQL Server at Microsoft. Eric was a Hive committer for contributions to Stinger and is a technology expert on data warehousing, column stores, and vectorized query execution. Thank you for joining us today, and welcome Eric and Dominic. You now have the floor.
Thank you, Alicia. This is Dominic. So thanks for joining us today. Here's the agenda and what we'll cover over the next 40 minutes or so. We'll look at anomaly detection from a couple of perspectives, and it's a broad category. So we'll give you a couple of customer examples as to how this is applied and help you understand how MemSQL helps to address these kinds of problems. And then I'll hand off to Eric to describe the next level of detail around MemSQL capabilities, and then we'll end with a short Q&A as Alicia described. So what we're all faced with in this day and time is how to manage data at speed and volume. And what we all see is that demands of data are growing across multiple dimensions. It's growing in data volume, and the variety and the complexity of data is growing. And businesses are looking to identify what's the most relevant data, along with determining context and meeting the expectation of customers. This is particularly difficult as data sets start to grow and customer expectations are such of having a real-time user experience for anything that they can access on a mobile device. And so what we see in the market is that the analytics are evolving from what was an after-the-fact sort of analysis on historical data to include current real-time data plus historical, and then add machine learning predictive capabilities or deep learning AI into the mix to help identify the golden nuggets out of that data. The problem is that systems are struggling to keep up with the complexity growth and the data variety itself. Over the past 10 to 15 years within the industry, there's been an approach to handle or meet these different types of workloads with bespoke or custom purpose-built kinds of data stores that handle one particular workload fairly well. And that works typically at small projects just getting going. But as the size and speed of data and number of sources increases, the cost of that IT infrastructure with multiple moving parts starts to increase. It's not just whether it's in your data center or in the cloud, this cost and complexity starts to increase steeply. And it's also the skill set needed for each of these specialized sorts of data stores or databases. And coupling with that, there's climbing concurrency demands, meaning multiple users, an increasing number of users wanting to access that same amount of data or calculations. So MemSQL uniquely addresses this and in a way that we call the database of now. And that is the current moment, whatever that moment, that business moment may be. It could be over a 5-second time window. It could be over 20 minutes. It could be the last day. It depends on the context and the use case and scenario. But what we do is we bring these capabilities together to provide speed, scale, ANSI SQL, and simplicity to a solution that can provide instantaneous calculations across lots of different data types. And so we're a distributed database that's cloud native, providing full ANSI relational SQL. And the benefit of that is that your queries have very broad expressive quality. And we'll cover this a little bit later in the context of time series and geospatial in particular. Secondly, data is not just a few particular data types. There are new styles of data access and data storage, such as document and JSON. We support these styles natively, along with relational structures. And when you're doing calculations that require time series for smoothing or geospatial, you can do all of that all within MemSQL. And we're also providing a feature which we're delivering over a series of releases this year called Single Store, which combines a row store and column store so that you can do OLTP or online transaction processing workloads with OLAP analytics workloads on the same table type within MemSQL. And then finally, we're optimized for real time. And this involves the whole life cycle of the data that is under MemSQL's management. From the moment it's ingested, it can be done in parallel and distributed fashion from distributed sources, such as Kafka and Spark. And when we're computing and storing that data in MemSQL in our distributed, within distributed cluster, you can do joins across this. And so these three capabilities are what support and allow you to realize the database of now. So let me give you a couple of examples of how this is applied in particular for geospatial and time series. So True Digital is the analytics division of True Corporation in Thailand, who's a large communications and media provider in the region. When the pandemic broke out, they, in cooperation with the Thai government, were looking for a way to identify proactively where the next viral outbreaks might happen so that there could be preventative measures rather than after the fact. There's a lot of public health information provided after the fact in terms of new testing that's more widespread. But to get ahead of new outbreaks, there's a need to identify if people are adhering to the social distancing. So essentially what they're doing is calculating social metrics in real time. And so the features of MemSQL that are used here is MemSQL pipelines, which I mentioned, provide you parallel distributed ingest, which allows them to ingest raw telecom data based on cell phone ping information to the rate of roughly 500,000 events per second for over 30 million subscribers. With that, they're adding geospatial reference data, which includes political boundaries, districts, states, that sort of thing, across the country, neighborhood information, such that they can do geographical queries against this real-time data. And it's for in the moment data, but also for some period of retention over a series of days and weeks to help with contact tracing where needed after the fact. This is an evolving solution, but all of this data is calculated live as the data is streaming across the network. So in a second example, in financial services, MemSQL has a customer who's a major US bank who's using the speed and scale and SQL of the product to do real-time fraud detection within 50 milliseconds. So this is doing multiple feature extraction across, doing multiple queries for features with roughly 70 values in the feature record within a very small time budget, and it's in line with the credit card transaction. So it requires a super high speed access to the data. And the flow provided is in line with the transaction, such that a request comes in to the online transaction processing application. And these queries are sent to MemSQL, which provide particular attributes or features from the data set. And so in this function, in this way, MemSQL functions as an operational data store. And these results all have to return within this small time window of 50 milliseconds, such that those that set of transactions that have been identified can be sent on to a scoring service that assigns a score for this. So you can think of it as MemSQL acts as a smart filter in this application architecture to identify, to sort the noise from the signal. So with that, I'd like to hand it to Eric to describe some of the features in MemSQL that support these kinds of use cases and applications.
Thank you, Dominic. So continue along the lines that Dominic was describing. I wanted to give my take on where MemSQL really shines for data analysis involving time series and geospatial and other types of applications. So MemSQL's one of the defining features of MemSQL is its very fast interactive response time. So we compile queries to machine code. We have a plan cache. So when you submit a query to MemSQL that's already been run before, if it can run in milliseconds or even a fraction of a millisecond. So it's super fast and interactive. So the next important characteristic of MemSQL is scalability. MemSQL is a highly scalable, scale out, shared nothing architecture database management system. So we can gang together multiple servers into a cluster, split the data across multiple nodes to handle arbitrarily large databases. So we have customers with over a petabyte of data under management in a single cluster. Also, we're excellent at simultaneous streaming, load, and query. MemSQL has multi-version concurrency control, and so readers and writers never block each other. And it's architected so you can load data fast and query it fast at the same time, and the queries and loading process don't interfere with each other. MemSQL, because of these capabilities I described with fast interactive response time and query compilation, were fantastic for real-time dashboards. So imagine a dashboard that has like 30 widgets or gauges or little charts on it, and each one has a query behind it, and that query is being run every few seconds. MemSQL is fantastic for that kind of use case because it can run the queries really fast, and once the queries are compiled to machine code, they just run amazingly fast. So you can increase the refresh frequency on a dashboard and still get very nice fast interactive response time, refreshing say even once a second with multiple queries running on a dashboard. We can do transactions and analytics in one system. So we have the ability to process queries very efficiently on both for individual row lookups and large group by aggregate type queries that are summarizing data. And finally, we have high availability and disaster recovery. So all these things put together, really enable MemSQL to shine for those real-time analytics use cases in particular. Next. So MemSQL does have built-in capabilities for time series data management. But first, every time series data management application is first and foremost a data management application. So the basic fundamental characteristics we have for data management, are helpful for time series apps too. So we have a full SQL implementation. We support transactions. You can do begin, commit, rollback type operations to support transactions. We have very fast and easy ingest capabilities to get the time-oriented data into your system. We support data compression. So if you've got very voluminous time-oriented data, we have a column store table type that has excellent data compression, can store very large volumes of data economically. We also support very fast query and vectorization. As I said, we compile queries to machine code. We also vectorize query execution on column stores, meaning we use single instruction, multiple data instructions, and process blocks of data in a really tight loop during query processing to enable us to do, process individual rows in just a few machine instructions each. So get very, very fast response time that way. And we do have built-in time series and time management capabilities. There's a bunch of built-in, there's several. We support a date time data type with resolution down to microsecond, and we have built-in operations for operating on time information. And some interesting ones are time bucket. And so time bucket is a function that can bucket information. You can bucket a timestamp down to whatever desired window you want, like 1 second, 5 seconds, 1 minute, 1 hour, 2 hours, etc. And then first and last are regular aggregate functions that give you the first and last value that was seen. And that can be very, very useful for finding temporal information in a convenient way with a query that's easy to read and understand. And I'll give an example later. And window functions are extremely powerful and advanced characteristic of SQL to do things like moving averages and so forth. And finally, we have extensibility capabilities with stored procedures, user-defined aggregate functions, and user-defined functions. So you can use user-defined aggregate functions to build new statistical functions if the built-in ones in MemSQL are not exactly what you need. Next. So I want to just give a little example that people can identify with about using time series functions in MemSQL. So many of you may be familiar with candlestick charts. So in stock trading, it's common to have what's called a candlestick chart as a graphical illustration that shows a time series with high, low, open, and close values for different securities over a moving time window. So you might have want to show high, low, open, and close for each day or for each hour, even each 15-minute period, something like that, as a way to sort of visualize the movement of data and the volatility of the data. So this is a graphic showing an actual candlestick chart plot. And now I'll show you a query that can gather this information. So this query is processing against a single table tick, and it's able to, what it does is it buckets by 1 hour intervals, and then it finds the high, low, open, and close during that 1 hour. So that would be the min and max values are for the high and low. And then to get the open and close, we use first and last. So that those first and last aggregates know what the time value is of the data. They know that it's TS. And so that they don't have to reference both the TS column and the price. So they're finding the first price and last price ordered by the timestamp TS. So this same exact query can be written with window functions, but it's quite a bit harder. It takes like 4 times more lines of code, and it's a little more sophisticated. So this helps experienced developers just be more productive, and it also opens up the capability to process time series data to maybe less sophisticated developers or with less experience. Next. And in addition to our geospatial capabilities, we also, in addition to our time series capabilities, we also support geospatial operations and geospatial types. So MemSQL supports these types of geospatial objects as column types, polygons and multi-polygons, paths, and points. And MemSQL incorporates functions from the Open Geospatial Consortium for performing operations on these types. So I described the data types that we support that are geospatial. We also support the well-known text format for geospatial object representation. We have a collection of topological filter functions like, contains filter functions that you can use as predicates in the where clause of a query and so forth. We support the ability to index geospatial data. You can create a geospatial index on MemSQL tables. And we have measurement functions to calculate, say, the area of a polygon and so forth, and you can use those anywhere you need in a query in the select list or the where clause, for example. And we support spatial joins via some of these spatial predicates. And moving on to anomaly detection. So some of the approaches you can use to do anomaly detection with MemSQL are, first, you can use built-in statistical functions. So we support min, max, average, median, standard deviation, percentile. So all those standard statistical functions can be used to detect outliers, using standard statistical techniques. We support integrated machine learning capabilities. So you can we support a pipelines feature, which has something called a transform. You can score data on ingest using a pipelines transform in MemSQL. So if you have a trained model with Python, for example, you can create a Python transform that invokes your model on a record that's coming into the system and computes a score that's then loaded as one of the columns in the data that you're loading. We also have integration with Spark for both training and scoring. In addition, we have vector matching functions for deep learning applications. So those that are using deep learning to do things like image recognition can extract a vector that represents a thumbnail sort of representation of an object. And then you can use built-in functions in MemSQL like the dot product function or Euclidean distance function to gauge the distance between two objects by doing a vector comparison. So we have a few customers that are using this in production now to do image matching type applications. And I wanted to come back to one of the important capabilities that Dominic mentioned earlier about using MemSQL as a real-time operational data store to enable you to gather a feature record or that you can send to your application code to score, but do that in an incredibly fast, real time. So you can run with, dozens of queries in a few milliseconds, grab the results, assemble a feature vector, and send that to your application code to score. And what that does is it enables your app to, use a more up-to-date and fresh feature vector, and you can now allow you to do a better job of things like fraud detection. And that was what was done in that banking example that Dominic mentioned earlier.
Great. So I'd like to show a couple of examples here. First, I'll start with a simple example of a geographical query. And this sort of shows how concise you can identify a point within a particular geography where you've got a polygon that represents a neighborhood or a borough or a city or that sort of thing. And you can, whatever geography you want to generate, you could store that in the geographic data type that corresponds to that in MemSQL and query against that. And so this is fairly straightforward, and there are several examples covered at docs.memsql.com in the geospatial guide. And you can see more complex examples of this. So in the next example, I'd like to show how one of the anomaly detection techniques that Eric cited, namely built-in statistical functions, can be used for anomaly detection. And so what you see here is a query that uses two common table expressions. And this is against pediatric children's age and weight. So the result of this query will give you the deviance from the median weight of the preschoolers. And what's interesting about this query is that it uses a couple of capabilities from MemSQL. First, common table expressions. Two of them you see here, median tab and the dispersion tab, or median table and dispersion table. And it's using percentile to determine a statistical threshold for these weights. And so this query is basically represents what workers in non-parametric statistics for public health would identify as a child close to the median. And so what's being calculated essentially is a median absolute deviation. And that is one common means of identifying anomaly across the data. And it's a little more robust than using z-scores to find these outliers, because this method doesn't make an assumption regarding the distribution of the data. And so as you can combine these techniques that we've described so far of time series, such as time bucketing, smoothing of data, along with window functions across time and geospatial queries, to do very sophisticated computations and queries to determine the context of what's normal in a given business scenario and what's anomalous, along with just statistical functions like I'm showing here. So all of this provides better context and allows you to determine on raw streaming data what's the best action to take and what's happening in the now, so to speak. So with that, Alicia, we'll open it to questions.
Great, thank you. Okay, great. So we have a few questions that have come in so far. And as a reminder, you may submit questions through the Q&A function located in the lower right side of your console. So let's start with this one. You mentioned you have a row store and a column store. Are there any special requirements for time series analysis depending on table type?
Yeah, I can take that one. So yes, MemSQL, you can use excuse me, can you repeat the question?
Yeah, no problem. You mentioned you have a row store and a column store. Are there any special requirements for time series analysis depending on the table type?
Yeah, for time series analysis, there's no special requirements, that you can use all the time series capabilities that we talked about, like first, last, time bucket on any table type.
Okay. Great, thank you. Are there any special requirements for spatial data depending on the table type?
Yes. So you can run spatial queries. You can put spatial data in any table type. You can run queries that involve spatial information, against column store or row store tables. But if you want to have a spatial index, you need to use a row store table.
Great, thank you.
So that means for very fast, highly selective lookups that involve a spatial predicate, you'll want to use a row store.
Okay. This one is a bit of a long question, so let me know if you need me to repeat it. I noticed that you are using terms such as time series, historical, and temporal interchangeably. I think they are not interchangeable and represent distinct concepts and applications. Are you saying that MSQL provides all those functionalities?
I think that that's a good point. I mean, we do have built-in time management capabilities that some people consider time series capabilities. That's the way we view the time bucket first, last type operations. And we know that you can perform time series oriented operations on the time oriented data with window functions. So I think that different people might treat that terminology differently. That's about all I can say about that one.
Thank you. Please address continuing activity and resyncing with respect to distributed databases following network interruption.
Okay, so I think that question is asking about our high availability and disaster recovery capabilities. So I can talk a little bit in general about our HADR capabilities. So MemSQL has built-in high availability. So as I said, it's a distributed system. Data in a MemSQL database is spread out across multiple nodes called leaf nodes. So it's partitioned across the nodes. And we have high availability based on a concept of what we call redundancy 2. So that means there'll be 2 copies of each partition, one copy on 2 different nodes. There'll be a primary node and a secondary node for each partition. So if we lose any one particular node in the database, we have high availability, so we'll fail over that node's work onto another node. So normally, because MemSQL, it is a distributed system, but it's a single cluster is all in one local area network and usually connected to the same network switch. So, network partitions, just essentially don't happen in that environment. If they did happen, that means basically your network is down and the system would detect that and would become, it would become non-operational. But if you lost a single node because the hardware for a single node failed, for example, or like one port on your network switch went bad, you would fail over the work from that node to another node, and it would, the system would continue to work uninterrupted, and the application would continue to be able to query and update the data. Now, what I just described was our high availability capability. That's all within a single MemSQL cluster. And for disaster recovery, we have the ability to create a replica of a database on a second cluster that's located elsewhere on the network. So it could be in 2 different locations connected by a wide area network. Like you could have one cluster in Manhattan and another one in New Jersey, for example, and do disaster recovery between the 2. And so that a network partition could happen in that case, and the replica would get behind the primary. But when the network came back, the replica would catch up again.
Great, thanks, Eric. What language or languages does one write UDFs in?
Sure. We support a built-in programming language for writing stored procedures in UDF called MP-SQL. It stands for MemSQL Procedural SQL. And it's our own language. It has a lot in common with the stored procedure syntax that you can find in both Oracle and MySQL, but it's our own language. But it's syntactically quite similar to the to PL SQL in terms of the control structures.
Thanks. How do you combine time and space together when a query requires that?
So you can combine time and space together. Like, for example, you could, have a series of events coming into a system that might have both time attributes and spatial attributes. For the time attribute, you could have, say, a timestamp column TS that was a date time 6. And you might have another column which was like a point where an observation occurred, and another column which is a value that was measured in that observation. So using SQL window functions, group by, aggregate, where clause, whatever you need, you can reference either the time, both the time and spatial elements to combine those kinds of information in a single query.
Okay, thanks. And do you have integrations with existing custom proprietary database management systems?
So we have. I'm not sure where that question is going. I can just say that we have the ability to integrate with a number of different data sources. We have a partner that we work with that has a tool that can allow us to ingest data from external databases, and we have. So that's probably the best answer I can give about that.
Okay, thanks. Can we integrate our own machine learning or deep learning model?
Yeah, I'll take that one. So we mentioned earlier the MemSQL pipelines, which is our parallel and distributed ingest mechanism. And you can think of MemSQL pipelines as a way to do data integration. So but it's not external middleware that you need for that. So often our design pattern is to ingest the raw transactional data from the source, often a distributed cloud source, such as Kafka or Spark. And in the process of ingesting that data with MemSQL pipelines, there's a capability which we call MemSQL pipelines transform, which allows you to call your external machine learning model. So if you have a trained model, let's say it's in AWS SageMaker, for instance, then through MemSQL pipelines transform, you can call that trained SageMaker model to get a score. So you can get an anomaly score. So you might have a trained model that's using random cut forest or an isolation forest mechanism algorithm to do this. This is pretty common for this kind of machine learning anomaly detection. And what that returns is a score on the level of anomaly in that data. When that data is ingested into MemSQL, it now has this calculated column or this additional field that's with the anomaly score, and that's written to either a MemSQL table directly or into a MemSQL stored procedure where you may do additional functionality.
Great. And it looks like we have time for just a couple more questions. So if we don't have a chance to answer yours before the webinar is up, then we will definitely be reaching out to get all of your questions answered. How many events per second can you load into a MemSQL time series?
I'll take that one. So really, that's just boils down to how many rows per second can you insert into a table in MemSQL? And the answer is millions. If we on a medium-sized cluster, say with 8 nodes, you could, depending on the application and the nature of the data, you could easily load several million rows per second.
Great. Thanks, Eric. Thanks, Dominic. Thank you, everyone, for all of your questions. Unfortunately, that's all the time we have for today. And so for those of you with questions we didn't get a chance to address, we can follow up with you directly. We also have a short survey followed by the close of the webinar and appreciate your participation. If you can stick around for an extra minute. I want to thank Eric, Dominic, and each of you for attending today. Just a reminder, we'll be sending you a follow-up email with a link to today's recording and slides. If you have any questions in the future, you can send us an email to team@memsql.com. We invite you to learn more about memsql at memsql.com, or you can get started for free today at memsql.com/free. Again, thanks for participating and have a great remainder of the day.